Okay, so to start our discussion about the gravitational potential, let's come back and remind ourselves of how the gravitational force relates to the gravitational field. So we said the gravitational field is basically the gravitational force where I'm dividing out the impact of my test mass. And so one of the things that we emphasized about this was that the force depends on both the source mass and the test mass. It depends on two masses. The field, on the other hand, only depends on the source mass. And what we're going to do is we're basically going to play exactly the same kind of game in relating the gravitational potential to the gravitational potential energy. So the definition of the gravitational potential is that it's the change in the gravitational potential. So V is going to be our symbol for potential. The change in the gravitational potential is equal to the change in the gravitational potential energy, where again I'm dividing out the test mass. So my gravitational potential energy depended on two masses. Right? We called them M1 and M2 at the time, but we could just as easily have called them source mass and test mass. And what I'm going to do is divide out one of those masses. So what I'm left with is something that only depends on the source mass. So I'm going to talk about the gravitational potential. And again, in the same way that the potential energy, I had a source mass and then a test mass sitting at some point. The potential is just going to have the source mass and the point. I'm not going to have that second mass. So in terms of what we did previously, in defining the change in the gravitational potential energy, we said, oh, well, that's this integral that involves the gravitational force. And what I've got here is the gravitational force divided by the test mass. Well, the gravitational force divided by the test mass is nothing more than the gravitational field. So my definition for the gravitational potential, the change in the gravitational potential, is negative sign still there, an integral from some initial position to some final position, and then now I want the dot product of the gravitational field with my tiny little infinitesimal displacement. Okay, so if I have a constant gravitational field, and one that points downward, again, say at or near the surface of the Earth, then we went through and said, oh, the change in the gravitational potential energy I end up getting by this mg delta h. And again, if we want to talk about the gravitational potential energy, that means I need to pick a point in the case of a constant gravitational field where the gravitational potential energy equals 0, and then I can talk about the gravitational potential energy using this equation. So the plus or minus tells me whether I'm above or below my 0 point, and then these are all defined to be positive scalar quantities. If I want to talk about the change in the gravitational potential within this constant gravitational field that points downward, well, the easiest way to deal with this is just say, okay, well, it's just the change in the gravitational potential energy, but divide out the test mass. And again, here is my test mass. So this is the mass that I've placed in the gravitational field caused by my source mass. So when I divide that out, what I get is g delta h. And so in the same way that we said, hey, if you go up, delta h is positive, so your change in gravitational potential is positive. If you go down, delta h is negative because your final minus initial in heights, the initial height was larger than the final height, so delta h is negative, then your change in gravitational potential is negative. If you want to talk about the gravitational potential, well, again, it's defined in terms of how it changes. So to talk about the gravitational potential, just like with the gravitational potential energy, we've got to be able to define a 0 point. And here we're going to pick that the gravitational potential energy, or the gravitational potential equals 0, where the gravitational potential energy equals 0. And so now I can set up a fairly simple equation where, again, you notice the only difference between here and here is that I've just lost this mass. So the gravitational potential only depends on the source mass, and the source mass is hidden inside this field. right? So the source mass is what's creating the field. That's how the gravitational potential only depends on the source mass. And then where you are relative to that source mass is again going to dictate your potential. The potential energy cares about not just the field generated by the source mass and where you are in that field, but also the second mass that you put there. So if I double the mass that I place at the same spot, I actually double the gravitational potential energy. But I haven't done anything to change the potential because I'm still at the same place within my gravitational field. So for a gravitational field due to point masses, well, again, we've got the same starting point, right? So here's our definition, and we know what to do with this gravitational field for a point mass. We know that what the mass wants to do is, again, it wants to move. So if you put a mass here at point P, so again, point P is just a point in space, but if you put a mass here, it would want to move in this direction. So we know that if I let that mass move in this direction, I'm going to decrease the potential energy. If I make the mass move in the opposite direction, I'm going to increase the potential energy. And so what's happening with the potential is easy to figure out because I know what's happening with the potential energy. And the fact that my mass is always positive means that the sign of the change in potential energy has got to be the same as the sign of the change in potential. So if I put a mass here at point P and move it away, I'm going to increase the potential energy. That means moving away from my source mass must increase the potential. So moving away from the source mass increases the potential. This tells us that what mass wants to do is move from high potential to low potential. It wants to move from far away and get closer. So mass wants to move from high gravitational potential to low gravitational potential. Doing that decreases the gravitational potential energy. That's what's always going to happen when you let your system go, is it's always going to work to decrease its potential energy. And in this case, it does it by that mass, by any mass that you put out here, moving from a high potential point to a low potential point within the field. All right, so to just go through the math now, sort of conceptually talked about what's going on. To go through the math, well, we know how to calculate the gravitational field. It's just given by g ms over r squared in terms of its magnitude. It's going to be negative here because it's pointing back to the left, and we've said to the right is positive. My two minus signs are going to cancel. My g and the mass, those are constants. I can pull those out of the integral. And so again, when I do my integral and evaluate, I'm left with this expression. And you notice that this expression, the only thing that's different here from what it was when we were talking about the change in the gravitational potential energy was that there was a second mass term. So again, we've just divided out that second mass term to get the change in the gravitational potential. We only care about the source. If we want to talk about the gravitational potential in this situation, well, again, we have to have a place where we can say the potential equals 0. And just like with the potential energy for a point mass, that happens to be when you're infinitely far away. So the gravitational potential equals 0 when you're infinitely far away from your source mass. So if we set our initial equal to infinity, we let r become our final distance from the source mass, and then we're left with an expression to calculate the gravitational potential is just minus gm over r. So this is how we're going to be able to calculate the gravitational potential due to a point-like source mass at some point P. All right, so what is this equation telling us? So again, important points about the gravitational potential due to point masses. So this is valid for point masses or anything that we can treat as a point mass. And it says, well, again, this is never positive. It's 0 if you're infinitely far away. It's non-zero if you're not. Or it's negative if you're not. So never positive. To increase the potential, again, means that the potential is becoming less negative, and you do that by moving further away from your point mass. So the farther you get from your point mass, the greater the potential energy is. So you're increasing the potential energy by moving farther away. But you still have a negative number. The potential depends on only one mass. This is like the gravitational field, because again, how did we get this? We did an integral that involved the gravitational field, not the gravitational force. So our gravitational potential depends on one mass, just like the gravitational field did. Again, the potential is a scalar. Right? Our dot product got rid of the vectorness of the field, and so the potential is a scalar. And again, just like the potential energy, the potential goes like 1 over r rather than 1 over r squared. So our energy terms, both potential energy and potential, those are 1 over r. Our vector terms, force and field, those go like 1 over r squared. So if we're calculating the gravitational potential at some point due to multiple point masses, so here's I've got multiple source masses that I need to consider, and basically all we're going to do is just, well, every source has a contribution, and we just need to calculate what the source or what the contribution from each source is at point P. So the gravitational potential at point P is just going to be equal to the sum of the gravitational potential at point B due to mass 1 plus the gravitational potential at point B due to mass 2. So I simply have two terms that I have to go and calculate. And so again, calculating the potential at a point is only going to basically depend on, I'm going to have one term for each source mass in the problem.